Thank you. Hello, everyone, and welcome. My name is Matheus Guimarães, aka Coding Matheus, everywhere online. Follow and subscribe. I am here to talk about generative AI. I bet you never heard of that before, yeah? A very obscure term. But the good news about generative AI is that however junior it may be, however senior it may be, it is new to most people, right? And it keeps changing so fast, evolving fast over the time. So it's not even looking like it was in 2022 when it became mainstream. So there's a lot to discover, a lot to keep up with. And a lot of people are in different stages of this journey. So what I want to do today is make sure we're all on the same page. We're going to cover some concepts and terminologies that you may or may not have heard of, demystify some of those. And then I'm going to just show you very quickly how it looks like on AWS and how you can use them programmatically. Okay, but strap to your DeLoreans because our journey starts all the way back in the 1940s when this incredible man did one of the earliest, if not the very first, talk on machine learning and artificial intelligence. Anybody knows who that is? Yes?
Alan Turing.
Alan Turing, Mr. Alan Turing indeed. And Alan Turing, while there were all the distractions from World War II, and he was at Bletchley Park, he started thinking about machine learning and artificial intelligence. And he shared his vision and his theories with his colleagues there. And then once the war was over, he then collected all that into that first talk in 1947, where he said that what we need is a machine that can learn from experience. And the way to get there is by finding some way of having the machine alter its own instructions. Then he matured those ideas, and in 1950, he then published his paper in Mind. That paper was huge because it proposed many things, including the very famous imitation game. There's even a movie about it, and which is more famously known as the Turing test, which can use to prove if a machine truly is intelligent and can fool you as a human. But in that paper, he also proposed many of the things and advancements we had in AI over the decades, and still apply today. So incredible man. And it's because of his work that I inspire other people to continue on doing AI. So the very first AI program ever written, followed by Turing's work, was in 1951, and that was by Christopher Strachey in the University of Manchester in England, where he wrote a bot that could play checkers. And that started small, but by 1952, it could play a full game of checkers. That was followed not too long after, in November, by the second AI program ever written, this time Dietrich Prinz, also at the University of Manchester. I don't know what they were doing. They were having brain juice for breakfast back then in Manchester. And that one was a bot that played chess. Couldn't play a full game of chess. It was only reacting to certain movements, but certainly very impressive for the time, because chess has more complexity than checkers. And ultimately, everything comes down to video games, which pleases me a lot, in case you have not noticed. And then we're going to fast forward all the way to the 80s. AI continued to advance, but something way more important happened in the 80s, something huge that changed the world forever. And that was the fact that computers made their way into everyone's homes and offices. And that created a huge hunger for storing and reading information. So this exponential volume of data started getting worse and worse and worse, and bigger and bigger and bigger. So we had the IBM PC in 1981, which had only 64 kilobytes of memory, no internal storage. If you wanted to store anything permanently, floppy disks. And floppy disks at the time only supported up to 320 kilobytes of data. So we went from kilobytes to megabytes to gigabytes to terabytes. A lot of people have been on petabytes already. Some customers and people and companies are already on the exabyte. So what's going to happen when we reach the zettabytes? Well, you don't have to imagine, not just one zettabyte. How about 120 zettabytes? That's the amount of data that we are expected to generate in 2024 alone. Not sure how it's tracking now that we're going towards the end of the year, crazily enough, but I'm pretty sure it's there or probably even exceeding it, right? But the point I'm trying to make here is that this is too much data for our tiny little fragile human brains to cope with. So eventually we would need some help to break outside of human limitations, right? So visionaries and industry leaders like AWS have been looking at this for a very long time, and we've been advancing in AI for a very long time. So things like chatbots, translation systems, text generation, these are not new things. What's new and changed dramatically is the way we create them and the speed where we create the systems. But in traditional ML, this is how things worked. You have one model, and then it will do one task, and then you will optimize for the task. So you want a chatbot, you could have one, but you have to form a team of data scientists, then they will have to create a model, and then they'll have to optimize that for the kind of chats you wanted to have. You wanted to generate text, same thing. You gotta get a team of data scientists, hopefully the same ones, so you don't keep changing it, but they still will have to create yet another model and optimize for the kind of text you wanted to generate as well, right? And the way you will optimize those models was by doing label data. And label data is just a fancy term for tagging. Same thing, tagging data, labeling data, right? And you need that if you're gonna train your models using supervised learning. And it's pretty simple. The way this works is like this. You imagine you have two pictures of two dogs, and then you're gonna label them. You're gonna tag them with the words animal and dog. And then we're gonna give it to the machine. What we're doing here is saying, look, machines, learn from us. This is our understanding of the world as humans. Learn, and then you can go and do your thing. And because of that, the machine is gonna go, okay, human, you think these are dogs. Let me extract patterns to try to understand why you think this is a dog. And the next time we give it a picture of a dog, hopefully it gets it right. And of course, this is going by the clues that we're giving the machine. Now, the opposite of supervised learning is unsupervised learning, exactly. So it's not that difficult, just grammar. Unsupervised learning is when you do this training of the machines so they can acquire knowledge, but this time use unlabeled data, right? You're not giving any clues. So the way it works, you give those two pictures of the dog again, but this time you're not tagging it, you're not labeling it. So you're gonna give it to the machine and it has to work it out by itself. Of course, this is much harder for the machine, right? Because it needs to now figure out what is exactly the same, what is different, what is just similar, what is completely, out of the concept. And that means that it needs to pick out on very detailed nuances about everything. And that is why you may have heard from bosses, colleagues, or maybe data scientists, consultants, that if you're gonna train a model, you need a lot of data, right? Because it needs to be able to pick out all of this stuff. If I give a picture of a hairless dog, it has to go, okay, that's still a dog. It just doesn't have hair, even though most of them do, right? So you need a lot of data to do this. But as we already talked about, volume is not a problem. We have data coming out of our ears, right, for many, many decades now. So the question is how? How do you actually get machines to be able to process this much data and pick out all this, very nuanced details? Well, the answer was deep learning architecture. And deep learning architecture also has been evolving over the years, but the way it works is that it has many, many different layers. And each one of these layers pick out a different pattern. So very small nuances on things. And when you put an input through it, it goes through all those layers, and then when it comes out at the end, it collects the evidence and then makes a conclusion. That's a dog. I see what you're doing there. You can imagine deep learning architecture working kind of like if you come across a familiar smell, if you're walking around, the streets, and then you start drilling through your brain going, what does that remind me of? That's how deep learning architecture works. And like I said, it was evolving over the years, much like anything else. But then in 2017, something amazing happened. Groundbreaking that changed everything, changed our world once again, and started effective generative AI revolution. And that was the publication of the paper. Anybody knows? All you need is attention, except almost there. Attention is all you need. Exactly. Attention is all you need, changed everything. And this was done by these incredible 8 modern Alan Turins. These are your new Alan Turins. And yes, they worked at Google and it was published by Google. But, like I work for AWS, I think technology is made by humans and we should sing the praise of humans, not just the company. And also, interestingly enough, something happened to that paper last year, which I think set a precedent because it never happened before. It was amended. And the amendment was they crossed out all the emails because none of them are at Google anymore. and that is obvious because they are geniuses. They changed our landscape. And most of them have their own startups with hundreds of millions invested, figures why. And one of them is AI research, OpenAI, and all kinds of stuff. But these people change everything. Why? Because they published that paper, Attention is All You Need, and then from that they created transformer architecture. Transformer architecture is super cool, super geeky. In my book, one and the same thing, right? It's very difficult. It's a kind of material that you have to revisit many times until you fully grasp it, which is both a statement and a joke for those that understand recurrent neural networks. But I like a challenge, and I really wanted to at least expose you guys, whoever's not very familiar with transformer architecture, to why is this so revolutionary. So at the very least, you have some water-fountain conversation with data scientists, so they don't have a one-up on you. So yeah. So what I want to do is just tell you very quickly why transformer architecture changed everything. And these are three main reasons: positional encoding, self-attention, and multi-head attention. To understand what these things are, we need to look inside foundation models. We need to rip it open and look at their guts. So let's do that. This is how it looks inside a foundation model. At first, it can be very daunting, but it already becomes easier if you realize that it's just a pipeline. And like any pipeline, there's an input and an output. And the input, in this case, is your prompt, right? Now, what happens there after you send the prompt is that it needs to convert to its own language. It needs to kind of encode it to a language that's more familiar to the foundation model, right? So think like decimal to binary, right? There is a representation thing that is easier for the machine to understand. Previously, in traditional AI, whenever you did this encoding, these machine learning models, it will simply do that. Much like decimal to binary, it was just a different representation of the same information. But what transformer architecture did was add information into that encoding. So not only represents the data, the text of your prompt, but adds information about the position of what those words occupy in that sentence, right? And that is already hugely transformative, because a lot of the stuff here needs to know that position, the algorithms, right, to work out relevance, to work out what's happening there and give you good results. So this information is now rapidly available at any time, at hand, at any point in this pipeline when somebody asks for it. So that increases efficiency a lot already. And that is what is called position encoding. But wait, there is more, because of course, now we know the position of things, we need to understand the meaning of things. And the way this always worked was through something called attention mechanism. Very cool stuff. This actually simulates our own human attention, human cognitive attention mechanism. So it tries to simulate what happens in our brain. And what happens in our brain is like this. Right now, you're listening to me. You are dropping certain words. You are hanging on to certain words so you can keep up and learn and store it, right? So it emulates the same thing. And the way the machines do it is by applying scores to things, which is kind of how our brain does it, I guess. So for example, the word the is like, yeah, okay, because it doesn't matter that much. Oh, now you said a verb. Yeah, that's important because that probably dictates a law of what's happening here. So it needs to score these things. This is attention scoring, right? Part of the attention mechanism. Now, the problem is that previous attention mechanisms were very slow and inefficient because, one, it depended on a lot of modules like calls that it had to make every time it needed to work this out, right? Two, it had to do one at a time, sequentially. So it had a lot of stuff to do until you could actually get to a full score to then determine, what's happening there. Comes transformer architecture, boom! Everything that you need is in that prompt. Nothing else. You don't need to call external modules. You don't need all the algorithms. You don't need data points. You just need the prompt. And now self-attention allows you, that algorithm, to work out those attention scores just with that information. So they take it to the next level, and then they create multi-head attention modules. And multi-head attention, what it does is take full advantage of the concept that now all you need is the prompt to start parallel computing. Always the answer to everything. So you start multiple compute instances, send the full prompt to each one of them, but go, hey, you're responsible for calculating the attention score of this bit, you this bit, you this bit, you this bit. And that means that you're going at full speed and you're able to work out things hugely much more faster than you could have before, which means that now you can hugely process more data as well, much faster, much more efficiently. So multi-head attention and self-attention and also position coding are pretty much the fathers and the creators of the foundation model era that we live in. And foundation models, ultimately then, are just big machine learning models. They are trained on transformer architecture, and that could be full transformer architecture, partial transformer architecture, or a variation of it, but transformer architecture, which allows them to have vast amounts of knowledge because they trained on vast amounts of data. And more importantly, they can do many different tasks. So remember, with traditional ML, it was one model, one task, and that's it, right? And optimization. Now it's one model, many different tasks. Okay, cool. But then if you can do many things, how can you actually tell what you want to do? How can you actually tell these tasks apart, right? So this is where prompt comes in, and where prompt engineering is so important. Now, prompt engineering at first can feel a little bit patronizing. It's like, oh, it's about learning how to write English. Give me a break. But it's a bit more than that. You got to see that prompt engineering is about really honing the English. It's not even English-like now. It's just English, right? Not like when you had high-level languages like C, C++ come along and say, oh, my God, it looks like English now. I don't need to do assembly anymore. I started with assembly, different story. But it's actual English. But it is the programming language that you use to talk to foundation models, much like you use, Java to talk to the computer, which of course gets translated to machine code behind the scenes. So prompt engineering, you just got to see as that. It is English, but it is a programming language. And like any programming language, you want to take control. And there are many techniques, official techniques like zero shots and whatnot, that you can have a look at. But I do recommend you learn it because this is fast becoming a basic skill set that everybody's going to need. And not just tech industry, by the way, anybody. Like my sister is a prosecutor for the Brazilian government, and she's getting to prompt engineering. She's being asked to do it. So, everybody is already looking into this, so I really recommend you do that as well. Now, okay, I said that your prompt gets converted into this language. We just still don't really sure what that is. So let's look at what happens to your prompt. So your prompt you send to the foundation model. The first thing that happens is it gets sliced up, right? And it gets sliced up by this tokenizer. In this case, I use BERT because it's quite popular in many foundation models, but there are more. But in the case of BERT, what it does, it splits into these tokens that you can see here. And tokens, as you can see, are not actually words. They are many different types of tokens. So BERT, for example, will split this into under, stan, and ing. And the reason why it does that is two. One, because it needs to encounter things that it hasn't encountered during the training, so it can actually still learn about things. And two, because it needs to understand about flexion and grammar, right? So it needs to make a difference between plural and singular. If you send a prompt saying, I want an example, or I want examples, quite different, right? Type of computation needs to do. So it needs to understand those things. Now, BERT specifically has the CLS and the SEP tokens, special tokens, which denote beginning of input, end of input. And then there are other types as well. But the gist here is that tokens are not words. So if you want to calculate the amount of tokens your prompts generate, guesstimate from my end, personally I recommend just do your words and the punctuations and add the 20% on top, and then you get a feel for it. But the main question is, why should you care? Why do I even care about tokens and how many? Because they are a unit of cost in most hosted foundation models services, including AWS as well. It is important for you to keep track of this. For the input, you have to guesstimate. For the output, you can usually control via an API request by saying maximum tokens in my response is this. And you can do this even in the UIs, for these different foundation models, if you use, hosted services like that. But now we got tokens, we actually still need to encode into that language. What is the language? The, decimal to binary. What is the binary for foundation models? It's embeddings or vector embeddings. So these words are one and the same, right? So you can use them interchangeably. And it sounds really fancy, for if you haven't encountered, but they're really just another word for something much more simpler that I'm pretty sure is very familiar to you guys. Arrays. Very familiar with arrays, yeah? And so vector embeddings and embeddings are just arrays of numbers. That's it. But they're not just any number, they are special numbers. They are numbers that contain meaning, right? They map to something in your data. So you do this, much like with the tokenizer, you get tokens, you do this with vectorizers. So for example, you have Titan text embeddings for that. So if you put something through Titan text embeddings, it's a foundation model specialized in creating embeddings, it will derive these numbers for you, right? And map that meaning. So let's say, for example, we have a water bottle, I put it through Titan text embeddings, then it's going to generate that array for me that represents that water bottle. And each one of these numbers represents something. The first one, maybe it's representing a bottle. Second one, the fact that it's a liquid. Third one, the fact that it's water. And each one of these features is called dimension. And because we got 3 here, it's called a 3-dimensional vector. So see, we're putting up the fancy words. And you can have as many dimensions as you want. So you could have 1,000-dimension vector, 1,024-dimensional vector, which is right now the maximum amount of dimensions Titan text embedding supports on version 2. And of course, the more dimensions you have, the more you can describe an object or your data, the more accuracy you can drive. Now, there is a kind of turning point where there are too many dimensions and then the foundation model gets confused. Just like humans, too much information, and that's called overfitting. That's a bit more advanced. But, general rule of thumb, you want more dimensions. You want to describe your data as much as possible. And the cool thing is that once your model understands the world like this, it can now compare things using simple math, which is such a cool concept. So say you want to compare this water bottle to the Coke bottle, and we put it in a vector database which understands that these arrays are not just arrays. It understands they are special arrays. That's why you need a vector database. And you ask the vector database, how similar are these things? It's going to go, easy. They're not the same, but they're 2/3 similar. Because I've got 3-dimensional vectors here. 2 of them are the same, 2/3 similar. How cool is that, right? Cool. Now we know what makes foundation models tick. So let's have a look at the types that we have. So we have LLMs. They've been the start of the show for the longest time. I think you all probably interacted with at least one. So they're specializing text. Didn't take long for vision to come along. Those are foundation models that specialize in images, so you can work with them. But if you want to work with videos, videos are sequences of static images, but over temporal dynamics. So you need spatial temporal foundation models starting to come up, right? We're not there yet as a mainstream era, but it's starting to come up, many of those. Then you got graph models and speech and audio models. But the new star of the show is multimodal models. So taking over from LLM, stealing that thunder. Now, multimodals are models that can do not only multiple tasks, but they can deal with multiple modalities. What's a modality? Text is a modality, image is a modality, video is a modality, so on and so forth, right? Right now, they are at the text and image multiple modality, but who knows, all the things are coming up. And they are starting to come out of the oven like that. So Claude 3.5, all of the models in that family are multimodal, text and image, right? Llama 3.1 just came out in July. And they are not multimodal, but Meta was very quickly to say, we are releasing this multimodal very soon. So it's coming up very soon, right? So they are already going into this multimodal phase, all of them, and you can expect new ones to come out all multimodal as well, with Claude leading the way. And the good news is that you can use all of these in Amazon Bedrock, which is a serverless portal to all these foundation models, right? And Bedrock not just allows you to then use all of the Claude models we talked about, all the Llama models we talked about, but other ones as well, including ours. But we don't say you should use the Amazon Titan models because we don't believe one model rules them all. Within the same application, we have many customers that use different foundation models for different tasks, right? Or for different applications. Because each one will have its strengths, and you have to test them. You have to evaluate them to know which one is better. So Bedrock already gives you the facility to try different ones for whatever thing you need, but then it introduces a little problem because if you got all these foundation models to deal with, you need to learn their languages. Each one speaks a different language. Like anything in the industry, always, from CSS to JavaScript, everything has a journey of standardization because no one agrees on the right way to do things. So if you talk to Claude, it looks like this JSON-y, thing. If you talk to Llama, it looks like this alien little special syntax thing. And you need to learn their languages. You need to learn how to do this. And they keep changing as well with new versions. So that's a little bit of a burden and takes away from the experience of being able to switch very quickly between them that Bedrock allows it to do. So the second advantage of Bedrock is, and a big, big one that I think it's a huge differential to other things, is the Bedrock Converse API, which is a bit of a new release like just a few months ago. And that built a layer of abstraction over this specialized languages. So when you talk natively to them, you have to use the syntax. Otherwise, you just use Bedrock Converse API, and then you learn one way to do a request, one way to consume a response, and all you need to do is change between them with the model IDs, and done. Your code is super portable, very POC friendly, and you actually get to kind of compare apples with apples. So hugely powerful, supports tools and all kinds of stuff as well. So to conclude, because I think I'm about to run out of time, I've got 5 minutes. I probably, well, your clock is different than mine. I'm trying to, everyone coins a term, and one term, by the way, somebody coined was hallucination, which now, caught on. So this is when foundation models say the wrong thing, or they're too eager to please, just like humans. I hate that term. I think stupid, called hallucination. It's just an error, right? It's a generative AI type of error, like an exception that you have in code. But since everybody coins that term, now I want to coin a term as well. So I'm trying to get, like, instead of Gen AI, Gen API, I'm not sure how to put emphasis on this. But you see what I'm getting at. The thing is that all this advanced AI stuff, it has become just APIs, right? Sentiment analysis, all kinds of stuff. You can do it like using Amazon Poly, using Amazon Transcribe. You can do all this kind of stuff. Generative AI has come to that point. It is just an API for a developer. You can use the same skill set that you have today without learning anything new by using Bedrock, by using Bedrock Converse API. You just need to learn how to use that API, and you can add all this cutting-edge stuff to your applications today, just like anything else. It's super powerful, and people should start realizing this more, because all the stuff that we talked about here, they're good knowledge, good foundational model knowledge, because we are technologists, so it's good to understand those things. But really, when it gets down to the day-to-day job, if you just need to use it, honestly, if you go to Bedrock, it's just an API away from you to learn all this stuff. Gen API, however you want to call that. I had a little bit of code that I don't have time to show, but just so that you appreciate, in Bedrock, this is how it looks in Python, right? If you call invoke model, you are talking to the model directly. So you use their special language. This is what I'm doing here. I'm using Llama 3.1, and I'm using the special syntax calling invoke model. Now, Claude, as you can see, looks very different, right? Again, I'm using invoke model here, so that it looks extremely different because they speak different languages. Converse API, guess what? They all look the same. I have the same code here for both of them. The only thing I change is this, no joke, model ID. Find the model ID of Claude, find the model ID of Cohere, drop it here, you can use the exact same thing, and that request will, still be valid and work. So incredibly powerful, really recommend you guys looking at it. Thank you very much. Follow me online. I am everywhere, and I do a lot of tech content. So hopefully see you all online and around.